Good morning and welcome to Calculus in the AM. Broadcasting live on the second floor of the building. I'm your host, Mr. Stelka. Big shout out to Sarah, Lee, and Ava today. Quick review. The other day we looked at some strategies to evaluate limits. If possible, just do it without doing any algebraic, excuse me, without any manipulation. Sort of plugging in or whatever, substitute if possible. Remember though that in philosophically you're not really plugging in for this one, for example, 4 plus 3 is 7. We know that. You're actually thinking though that as x approaches 4, so 3.999 plus 3 is pretty close to 7, 4.0001 plus 3, as x gets closer to 4. It ends up being the same thing, but you're not actually letting x equal 7 philosophically. You're just plugging it in on that through. Sign analysis. Sometimes, if you can't see this, you don't have to do sign analysis on something like this, but sometimes to organize your thoughts it is. Undefined, if you can be more specific, if it's from the left or the right, you could say positive infinity, negative infinity, increasing without ending. It's infinity, it's not a number. Looked at a couple of those. Evaluating limits by factoring first. If you have indeterminate results, 0 over 0, it's possible, and you get a knack for this, it's possible that you can factor top and bottom, cross out a common factor. There's a hole there, you're thinking maybe. And then evaluate the limit. Lastly, we look at if you get 0 to 0, and it doesn't look like you can factor, simplify the numerator in this case, see what you get. Okay, I left this one here, but it would be the same kind of thing, and I had one in the textbook though for you to work on. Simplify in that case, it looks like the numerator. Chances are you're going to get something with x minus 3, it looks like. Well, who knows. Now, I'm going to pause for a second here. Okay, so new material now. Rationalizing. You try this, if you substitute, you get 0 to 0 in your head, you try that. And the expression has a radical involved here. Now what are we doing? Some people, what do you call that when you multiply by, in this case, the radical plus 3? Conjugates. Really and truly though, what you're thinking, you should be thinking as, this is undoing a different, or creating a difference of squares. Do you know what I'm saying? That's what conjugates are all about. So, in this case, I'm going to multiply the whole expression by the conjugate. To create a difference of squares on the numerator. Now, what does this have the effect of doing? Just remember the difference of squares. We added a minus b, a plus b. Put that up in green again. You guys are familiar with it, but you're probably more familiar with it where you're given something like x squared minus 64 and you work the other way around. And you've been doing this, though I know you have seen it. You'd have something like root 3 plus 2 or something like that, right? And you were always told you can't have a radical on the denominator. Is that correct? Here we don't care so much about that. It's just we got to figure out some way to get rid of this 6 minus 6 on the bottom. We can't evaluate it anymore. And I see something will happen. Now, on the bottom, I really don't care. This is just fine, this part. If I put 3 plus 6 there, that's 9, right? Root 9, so 3 plus 3 on the bottom. That's fine. Don't multiply out the denominator. As a rule of thumb, don't multiply anything out unless you're really certain you have to. We have to, though, on the top. Because, well, that's the reason why we put it there. So, knowing that you created a difference of squares, what does the top turn into? Well, it turns into the radical times itself, right? So it's just the inside of the radical. Root times root is what's underneath. 3 plus r. I'm going to put this in brackets. It doesn't really matter here, but it does matter if it was the second thing. And people are bound to make an error. They don't get into that habit, so that's why. So 3 and 3 is 9. There is no middle term because it would cancel out, right? The 3 radical 3 plus r minus 3 radical 3 plus r, it would subtract out. So, I almost forgot something. Very important, the limit notation. So that's the top. Can you see what the top simplifies to? It's not a big stretch, right? 3 minus 9 is minus 6. R minus 6. I think you could do this in your head here and here. That cancels out. What do we have on the top then, though? 0? No, it's 1, right? So that top turned into R minus 6, same expression. We got that. Now we can drop the limit notation because I'm actually going to evaluate. So that's equal to 1 over 3 plus 3 under a root sign. Honestly, I think you could have just done this in your head, right? Oh, 3 plus 3. R is approaching 6. Nobody stop me, guys. Okay, I'm on weekend mode still. So root 9, so 3 plus 3 on the bottom, 1 over 6. Okay. It's a good thing I had done it in my head ahead of time. 1/6, otherwise you're sitting there with an error. Okay, another radical question. This time it's on the denominator. X approaching 1, you can quickly scan it and see you'd have root 4 minus 2, so yeah, you'd have 0 on the bottom. Can't do this. And 0 on the top. Let's try out the old trick we just learned. Create a difference of squares. Plus 2x. And times on the top. Okay, I've created a difference of squares. Do not multiply it out on the top. So, keep the top as is. Work that out too. The bottom is a difference of squares because we created it that way. So the root times root is x plus 3 minus, here's, oh wait, what do we get there? Okay, we have the error I didn't want to hear. It's not 2x, it's 2 times 2, root times root, so 4x. Now, fly the screen. I'm going to simplify the bottom a little more. You probably can see it. Well, maybe you can't. Well, that's why I'm simplifying. Trust the process. So, x minus 4x is negative 3x. Okay. Now you look at it. This didn't exactly help me. Hey, I think I'm going to do some scratch work here just because I got so much space here. I'm going to use it. So, what is this if I factored out the negative 3? This is negative 3, x minus 1, agreed? So I'm replacing it, right? Like factoring it right there. Now you can see what we got cooking, right? Factor, and cancel the common. And I can jump in with some number now. I could drop the limit notation, say 1 plus 3, into the root sign. I'll just plug it in, I won't do the arithmetic yet. There you go, it's just arithmetic from here. Root 4 plus 2, 4 over negative 3. So negative 4/3. And proper fractions are just dandy. Okay, one last set of examples here. Evaluating limits at infinity for rational functions. So, here's the fact that we're going to use, and I think you knew this. As x approaches infinity, so 1 million, 1 billion, etc., it goes on to the right on a number line. You're looking at the graph of y equals 1 over x, that function. It's sitting at 0, getting awfully close. What we're talking about is this reciprocal function. It also works that way for negative infinity, right? And you think about it, 1 over 100 is 0.01. 1 over a million, 0.000, 1. It's really close, even the negative side it does. So the trick is to manipulate stuff so you have 1 over x involved, and then you laugh at it, okay? Cry, laugh, whatever. Divide the numerator and denominator by the greatest power of x that appears in the denominator. I should say degree, I guess. You look for the highest degree from the denominator, though. Now, in this case, when the degrees match, okay, you get one particular case. So I'm going to just, underneath this one here, just say, we'll put it at the end. Okay. Degrees are matching, though, you'll note that. So what I do is I multiply, as mentioned, by 1 over a squared because of the bottom. 1 over a squared. 1 over a squared. So I'm multiplying top and bottom, dividing numerator and denominator by the greatest power of x that appears in the denominator. Well, dividing it is 1 over, right? Same thing. 6 divided by 2 is the same as 6 times 1/2. That's division in a sense. Okay? So that's what I'm doing now. Let's rip that through and see what we get. Limit of a approaching, this is negative infinity, but same thing, we're looking for 1 overs. Well, on the numerator, a squared times 1 over a squared is 1. Plus 1 over a squared. On the denominator, 2 over a squared times 1 over a squared is the number 2. Plus 3 over a times 1 over a squared is 3 over a. Minus 1 times 1 over a squared, so minus 1 over a squared. Now we wanted to get something like this because that's something I can deal with. Now, remember there's rules to these limits intuitively. You probably can guess there. This is it. I'm going to do the limit of the constant 1. Well, it's 1. I'm going to do the limit here, though. 1 over a squared is the function. Now, as you approach negative infinity, so negative 100, negative 1 million, what's that going to turn into? 1 over a million squared, basically, right? 1 over a negative million squared. Still going to be awfully close to 0, isn't it? Okay. The bottom will be 2 plus 3 over negative 1 million, negative 1 billion, etc. It's going to be awfully close to 0, isn't it? On the negative side, but it's 3 divided by 100, 3 divided by 1,000. You can think it through. Yeah, it's going to be 0-ish. And this is going to be minus 0 as well. Now, I want to show you something that you can't do. I hate doing that, but I'm going to, and then I'm going to erase it. Do not copy this down, but here's an error I don't want to see. 1 plus 1 over infinity squared 2 plus 3 over infinity minus 1 over infinity squared. I guess those are negatives, but still, this is incorrect now. Doubly incorrect, singular, whatever. Don't do it this way. Infinity is not a number, okay? What you got to do is consider 1 over an extremely, I guess, negative number, negative a million, a billion, and see this whole expression is 0, okay? Do you guys follow me on that? Do not write down anything like that. Instead, there, I'll just fix this up. Turns out to be 1 over 2, but I'll show you if you want to show your zeros. 1 plus 0. 2 plus 3 over infinity, well, that's plus 0, then minus 0. Now, like I said, you could just, if you see the zeros, just jump right to a half. I guess I'll finish it right here. Half. That's the biggest mess I've made so far. Gee willikers. It just so turns out, and did you guys know this? Hashim probably did, but when you have matching degrees, did you guys know anything about the asymptotes before? The horizontal asymptote? No? If the degrees are matching, and I don't care if it was a cubed, a to the fifth, whatever, you have a situation where to the left and to the right, you have a horizontal asymptote, or a limit of it as a or x approaches infinity, of the ratio of the lead terms. 1a squared over 2a squared, okay? So when the degrees match, let's just get that down. It's a shortcut. When the degrees match, and we're only specific to the situation where you're approaching infinity. Degrees match, and that's for the numerator denominator. Take the ratio of the lead terms. That's a shortcut, and you can use it. However, if you forget what it is, always go back to divide by the largest degree from the denominator, okay? How about this one? When the degree on the bottom denominator is larger, we'll still use this, the greatest power of x that appears in the denominator. So we'll see what happens here. So limit of b approaching infinity for, well, I'm going to multiply top and bottom by 1 over b cubed. It'll help me see something. When I do that, I get on the top 3 over b. On the bottom, I get 1 minus 4b over b cubed, so 4 over b squared. Hey, I could evaluate this. No more manipulation. What does the top turn into? 3 over b. It's 3 over a really large number. Would be, Mac? 0-ish, good. So we drop the limit notation. I'm evaluating, and I do not put the infinity sign anywhere in this. 1 minus, again, 4 over something squared, very large, 0. 0 over 1 is 0. Good enough. So we're good on this? Okay. We'll try the last one. Switch colors. This is, oh, going back to this. If the degree on the bottom, denominator, is largest, so denominator's degree, largest means, I guess that's an arrow more like a dash, not a limit kind of arrow. That means it's going to give you a 0. It's going to have a 0 horizontal asymptote. Okay? what you get. And it'll have a question. I just said that's like a dash there.
Oh.
I put an arrow there and I said, well, that's not like a. The answer is, maybe I'll put. The answer is 0. Okay? You can have a 0 horizontal asymptote. Last. What if the degree is greater on the top? There's all kinds of manipulation you can do. I'll just stick to this. You'll see. Well, we still do the greatest power from the denominator. Don't do anything else. 1 over x. 1 over x. I rip that through the item. So it's equal to this. All x squared over x. So that's equal to x plus 5. That's it. 1 minus 5 over x. Now when I do that, can you guys see this? Let's just take a look. I'll wait for a second to make sure we're all with. Now I can't put infinity in there. It's the idea of you're increasing without n. So it's going to be a very large number there, plus 5. What's a million plus 5? It's a little over a million. What's a billion plus 5? A little over a billion, right? It's still a very large number. The plus 5 makes it a little larger. But if it was even minus 3 or something like that, it wouldn't change it. It's still, the top is going to be huge, infinite, right? The bottom is going to be 1 minus 0. You guys all follow me on that? So infinity over 1, still infinity. Like, remember, infinity isn't a number. I'm sort of talking like it is. It is. It's a huge number. This is going to be positive. It's going to be going up without it. Now, there's scenarios where you have asymptotes that run on lines or sometimes take the shape of a parabola. We're not worried about those. We're just worried about positive or negative infinity. In this particular class. By the way, I'm not going to write a general statement for this. You've got to work these ones out. If I had just changed 1 or 2 things here, and I'll just show you. If this denominator had been 5 minus x, for example, and I'll write this down, it's a different problem, but if the denominator had been 5 minus x, everybody's with me on that? I would have had same top. 5 minus x, so it would have been 5 over x minus 1. It's really messy, but I'm going to get my point across here. So if I had a slightly different problem, what would the limit have been there? Well, let's think it through. Still would have been a billion plus 5, a billion plus whatever on the top. However, on the bottom, it would have been 0 minus 1. Now, a gazillion, a billion, or whatever, divided by negative 1 is negative, right? This particular blue, if it was a slightly different problem, it would have come out to be negative infinity, okay? So you do have to think these through. And there's no general shortcut that I can say for this. Now you got some questions to try. So part 2, and obviously finish up part 1 if you haven't.